Hello, Physics 1. All right, so in part 2 of Tuesday's lecture, we finally get to learn the last of the 3 fundamental principles that we cover in the Physics 1 class. Angular momentum. So angular momentum is a measurement of rotational motion. So the reason why we see this at the end of the Physics 1 series is we're going to combine our understanding of rotational kinetic energy along with what we know about the momentum principle and bring it all together. So you have done a lot of work to get to this point in the semester. So there's 2 types of rotational motion that we'll be talking about. So translational, which is orbital. So this would describe motion like the Earth's orbit around the sun. So here's the sun, and here's the Earth going around. All right, so then you have rotational or spin describes motion like Earth's revolution on its own axis. So when you have Earth spinning on its axis, then you have revolution. So translational and rotational. All right, so angular momentum principle relates a change in angular momentum to net torque. So torque is a new concept. So it basically means a twist or twist applied to the system. So just like the momentum principle that we've talked about previously related a change in momentum to a force, the angular momentum relates a change in angular momentum to a twist, a net torque, something that would be causing it to change. Physics is all about cause and effect and what is doing the cause. And angular momentum, just like the momentum principle, just like the energy principle, is indeed a conserved quantity. All of the angular momentum that has ever existed and will ever exist in this universe has existed from the moment of its conception. So you never get more or less angular momentum within the universe. Now, of course, I know some of you are investigating the idea of whether or not the universe is an open or closed system, which is a very interesting philosophical question, but not really a scientific one. So, could be if we find evidence to the contrary. Okay, so moving along, let's start by learning about translational angular momentum. So as the Earth goes around the sun, it is changing direction. And it's doing this constantly. So we talked about this when we talked about circular motion. By the way, orbits, planetary orbits around our sun are nearly circular. They're only slightly elliptical. There's a reason why they thought they were circular. It's because they're almost circular. Comets, on the other hand, have the shape of orbits that we typically see drawn in books. The reason why you see those exaggerated elliptical orbits drawn is to help you remember that they're not perfectly circular. But most, when you see this, here's the sun, here's the planet, this has been drawn in an exaggerated fashion. If you were to draw it, you would see it looks nearly circular. It just bulges just a little bit on either end. Okay, so that tangent over. And but for this particular analysis, we are going to assume circular motion, as it is nearly circular. I believe it only changes about 1.7% at either point. So could be off on that number. All right, so if we are looking at the Earth's motion, let's go ahead. Let's bring in some colors. I know one of you said you liked colors, so I've been trying to do more of that. All right, so we've got, let's say the Earth is here. So then we would have R1. We'll look at 4 points as it goes all the way around. R2, of course, the magnitude of each R is equal to the other one. Oh, paper cut. R3 and R4. All right, so at each location, it's going to have momentum. So P1 is equal to 0, mv 0. P2 is equal to minus mv 0, 0, going in that direction. And P3 is equal to 0 minus mv 0, and P4 is equal to mv 0, 0, and it's going in that direction. So what we can see here is that the Earth goes around counterclockwise when viewed from above, and this is true. The Earth does spin the Earth rotates counterclockwise. All right, so let's label these so we can easily refer to them. We'll call this part point A, point B, point C, and point D. So we can see from looking at this that the position is changing and the momentum is changing as you go around. Because remember, momentum is vector. It contains with it direction. So in this case, it's going up. This is why this is positive. In this case, it's going to the left, which is negative. This is going down, which is negative y. And here we have it going to the right, which is positive x. Okay, so this is the picture to keep in mind. When Earth goes from A to B, then the change in momentum is equal to minus mv 0, 0 minus 0 mv 0. So delta P, A to B, is equal to minus mv 0. So pretty big change. And this is, of course, due to the gravitational force. So due to F grav, Sun, and Earth. So we have studied this before in chapter 3. One of my favorite chapters. I love talking about gravity because gravity is so cool. All right, so we are moving on. So we've seen a big change in momentum. But doesn't it feel kind of constant? I mean, look at that. You've got the same R's all the way around. You've got a really predictable change. Okay, so that's something to think about. That's interesting. Okay, it feels kind of constant. It's changing, but it feels constant. Okay, so we should note something. All right, so we have our R. Oh, I should do this with colors. Our R vector and our P vector. And we've noted, or we should note, that there's something that is actually kind of constant about these, namely, they've got a 90-degree angle between them. That's pretty much true all the way there, and that's something we've talked about before with circular motion, that's the case. Perfectly circular motion, not true for elliptical, but definitely true for circular. Okay, interesting. And also, the direction of motion is constant. It's chugging along counterclockwise. I mean, it's changing direction, but it's just, I mean, it's not like it's going all over the place like a bumblebee's flight. All right, so you would not be incorrect in noting that there seems to be some constants. The constant quantity that we're alluding to right now is translational angular momentum. So note, traditional momentum changing, translational momentum not changing. So in this case, we have the translational angular momentum as it relates to the sun. So this is, I'll write it out for you, translational angular momentum of the Earth relative to the sun. There you go. So the magnitude of translational angular momentum we would have L translational is equal to R P sine theta. So this would be position. This would be momentum. This is the angle between them. All things that we saw here. So position, momentum, angle between them. All right, so let's do an example. And we'll look at Mars's translational momentum. So we want to calculate the magnitude of Mars's translational angular momentum relative to the sun. When Mars is at A and at B. And so what I'm referring to is simply, we're going to do this, but now we're going to use Mars values. Going from here to here, once again, Mars's orbit looks a lot like Earth's orbit, nearly circular. So the mass of Mars is equal to 6.39 times 10 to the 23 kilograms. The orbital period is equal to 687 days. And the distance to the sun is equal to 2.279 times 10 to the 11 meters. So, to solve for angular momentum, first, we need speed, because we're going to use that to get momentum, or the magnitude of momentum. So v is equal to d over t. The distance it travels, we're assuming a circle, so that's 2 pi 2.279 times 10 to the 11 meters. Mars takes 687 days, so we've got 687 days. There's a lot of ways to do this unit conversion. There's 86,400 seconds per day. So we get a speed of 2.4 times 10 to the 4 meters per second at location. So that's going to be true the whole way. And then at location A, the momentum is equal to 6.39 times 10 to the 23 kilograms. Remember, it's going in positive y, times 2.4 times 10 to the 4 meters per second. There's that speed that we calculated, and 0. So momentum is equal to 1.5 times 10 to the 28 kilogram meters per second, 0. The magnitude of momentum is equal to 1.5 times 10 to the 28 kilogram meters per second. Yeah. And so, going back to our new handy-dandy formula, the translational angular momentum of the sun is equal to r p sine theta is equal to 2.279 times 10 to the 11 meters times 1.5 times 10 to the 28 kilogram meters per second times sine of 90 degrees, which is just 1. And so the magnitude of the translational angular momentum relative to the sun is 3.4 times 10 to the 39 kilogram meters squared per second. And at V, the magnitude of r and p and theta are the same. So L translational sun B is equal to 3.4 times 10 to the 39 kilogram meters squared per second. Nice and easy. All right, so we will stop here. I'll see you for part 2. We're going to get some direction on this.